Hello and welcome back. This is week 2 of the summer session, Computer Science 3, CSCE 310. We're live on YouTube, of course, but remember, I'm not looking at those comments. Several people were commenting on Friday. I'm not looking at those comments to try to save bandwidth, so if you've got questions or comments, please go ahead and make sure that they are on the Piazza, a live Q&A on Piazza. Looks like it's kind of spotty today. If somebody could make it, I'll go ahead and make a new post here. Quality. Go ahead and respond to it. If the quality is bad, then how is the quality? Let me know, and I'll see if I can make it. Let me double check my settings really quick here. Okay. One second. I'm going to stop streaming. I'll be right back. Okay, we'll try that again. Go ahead and again, let me know what the quality looks like. Hopefully it's just a temporary issue here. But of course, we'll go ahead and try to push forward here. Okay. So we left off on Friday with divide and conquer approaches. And one of the things that we looked at was we revisited the closest pair of points algorithm. And I kind of set you up with a question over the weekend of how many points do you actually need to look at in order to determine whether or not what were the two closest points. So let me go ahead and go to my overhead here and remind you of what that was looking like. Again, what we did is we separated all of the points, and this is not necessarily the y-axis right here. It's just a split so that, let's see, good, somebody responded. All right, it improved, thank you, great. So this is not the y-axis here. It's just a split so that roughly half of the points are over here, n divided by 2 points over here, and n divided by 2 points are over here. And what we do is we recurse and we find the closest pair of points over here in the left side, the closest pair of points over here in the right side. And the base condition there is when you get down to 2 points, then by definition, those are trivially the closest pair of points. So suppose that we're coming back from the recursion, and we've got 2 points over here, which are among all the points over here. This is how we found these are the two closest points over here with a distance of d1, and suppose that there are 2 points over here with a distance of d2. Okay, so well, clearly, if these 2 points are closer together than these 2 points, then these are the two closest points so far. So we can go ahead and say that D is equal to the minimum of D1 and D2. Right? This is what we were doing on Friday. But the problem is, how do we combine these two solutions? That is, there are points, what about this point over here that might be closer, and now it's not to scale here, but what if this distance right here actually happen to be less than this distance? So that means that we end up having to go back to the drawing board and say, okay, for each pair of points over here, make a comparison to these points over here. But we don't have to do them all. I asked on Friday, at most, how many do we have to do? So let's go ahead and take a point over here on the left-hand side and zoom in and say that it's really, really close to the dividing point right here, right? And suppose that D was our minimum distance so far, and say these 2 points over here were a minimum of distance of D. They beat out the points over here. I still have to look at all combinations of this point with every point over here, or do I? Right? All I need to do is draw a half circle over here of radius D. And now I can say that, well, any point beyond that is going to definitely be more than distance D, so I don't need to consider that. I only need to consider points within a radius of D from this point over here. Right? So all I need to do is check out a very thin line of potential points over here on the right-hand side. Now you can use some geometry and you can come up with, well, absolutely how many points can I pack in to this little half semicircle over here? And I believe that the answer is actually 4, but that would require a little bit more geometry than I want to get into. So the usual way of presenting this is, all right, well, let's just be naive about it. We'll assume that the point is right on the line, and then we'll look at distance d over here, a distance d up, right, and then a distance d over. Now this is already, this point right here is already exceeding, it'd be like right out here outside of that radius already. So we technically don't need to check it. But we do need, as I put it before, we simply need to look at everything within this band right here. So that corresponds to a distance d all the way over. Right? And this is the point that we're interested in here. Go down another distance d, right? And then over a distance d. And so you can see, well, very easily from just straight up grade school geometry, that the maximum number of points that you have to look at on the other side. So assume that this is just on the other side, that this is just on the other side. The maximum number is going to be 6. So at most, 6 points must be examined. Now you got to be careful, that was for 1 point. So for each of the points over here on the left-hand side, then we have to examine at most 6 points. So instead of looking at n divided by 2 by n divided by 2, for each pair over here, for each pair over here, giving you something like n squared, or order n squared is what I'll say, we can cut this down to, for each point on the left-hand side, of which there are n divided by 2, we only have to look at 6 points on the right-hand side, which is, forget about the constant here, this is going to be order n instead. We get away from doing a quadratic amount of work and only doing a linear amount of work. That's the basic idea. Now you do need to be careful if you're actually going to program this, because you would have to set everything up so that everything is sorted according to the x-axis, and then everything is sorted according to the y-axis, so that you can exploit a binary search that, given this point that has a y coordinate of this, you only have to look over y, a certain distance over. So all you have to do is look at the things on the right-hand side, which to find the maximum number of points over there. Then you just basically have to use binary search to find that distance. Basically, how many points are over here? Well, I need to find the cutoff point of this one is greater than d distance away. This one is less than d distance away. Okay. So there are some, subtleties when you actually go to program something like this. We're not going to get into it because we don't have to program it, but you can understand that you'd be using sorting, order n log n sorting. You'd be using binary search to find all those potentially up to 6 points on the in the other partition that you have to do for each point over here. What I do want to do, however, is I want to set ourselves up to understand, is this an improvement? Okay. So let C sub n be the number of distance calculations, or comparisons to find out, is this distance less than that other distance over there, for the closest pair of n points using this divide and conquer approach. All right. So we already, the divide is easy. All you need to do is split it into 2 sets, 2 partitions, and make recursive calls to each one of those. Each set is only of size n divided by 2. Now, when you come back from the recursion, when you come back from the divide, you do need to conquer it. So what that means that you need to combine those 2 solutions, like we just talked about right here. That for each pair in the left partition, you need to examine at most 6 pairs, 6 points on the right-hand side. So, so for each point in the left partition, you simply need to make 6 up to, and it's not it's not exactly 6 every single time. There might be no points within a distance of D on the other partition, so you could get away easy and get lucky and not make any comparisons here at all. But we'll go ahead and assume the worst case scenario. You have to make all 6 of those comparisons for every n divided by 2 point on the left partition. So this is the for each of the n divided by 2 points, compare or calculate distance with at most 6 points. Right? And so you can say that this is 3n over here or something. Right? Doesn't matter, because what we're going to do is we're going to apply the master theorem. The master theorem again says that our coefficient out here is 2. We divide the list in half each time, so our b over here is going to be 2. And our d or our k, whatever you're doing, that this thing right here, this is f of n, and it's going to be theta n, right? This is a linear function. So our coefficient up here that binds this polynomial is simply just 1. So what's the relationship from a to b to the d? Well, this is 2 is equal to 2 to the first. So this implies that that the number of distance calculations, the number of computations, whatever you're counting here, is going to be theta n log n. Right? It's actually n to the d, but d here is 1, so it disappears, and we're at n log n here. Now, of course, you do have to set yourself up by sorting everything with respect to x, and also sorting everything with respect to y, so that you can potentially look those things up, and you can bind them using binary search and all that stuff. But using a good sorting algorithm, you're going to have n log n behavior anyway. Quick sort in the best case scenario, merge sort, tim sort, whatever you're using. You have to pay for that anyway, but it's going to just be a constant coefficient out here. Say 2 sorts out here, and then the actual recursion over here, and another n log n. So there's some 3 sitting out front here, but again, it's asymptotics. We don't care. Right? So this was a huge improvement. Instead of doing the naive thing of doing every single n choose 2 points, which is going to be theta or order n squared, we've now cut this down to n log n, which is very, very doable on the vast majority of inputs. Now, if you get into the septillions of points, this is still going to take you a while, but at least it's going to cut down centuries down to maybe weeks. It's going to cut hours down to seconds, etc. This is a huge speed up right here. Okay. All right. So, again, our observation out of this is that there are only a constant number of points that we have to consider on the right-hand side. There we go. Which gives us a recurrence of c sub n is equal to 2 c sub n divided by 2 plus some order n function. By the master theorem, this gives us, I'll do it, theta n log n. There we go. Yep. All right. Check for questions. Nope. All right then. So let's take a look at another application of this. Not this problem, but the application of the strategy, a divide and conquer kind of approach. And I really like this one because it's something that everybody understands almost immediately, and it's something that you can program right away, even in a computer science 1 course. But then when you don't get an answer, you think, what the heck's going on here? And how long is this going to take? And by the way, I mean, I thought computers were faster than this. So What I'm going to do is I'm going to motivate this by I'm going to give you a task or a challenge. All right. Compute a to the n mod m for, for large n. And I don't know what I mean by large yet, but we'll go ahead and figure that out later. Okay. Now, this mod m here is just a red herring. We can take that off if you want. I'm doing mod m here to keep it small so that we, instead of looking at big giant numbers with hundreds or thousands of digits, we can keep it small and say mod 100 so that we can only look at 2 digits to see, is our answer right? We can check it against some known solution. Right? I'm also going to keep a small here, and I'm also going to keep it so that it's non-trivial. I'm going to choose a prime generally, because if it's 0 or 1, then we're done. If it's 2, then powers of 2, well, that's just a bit shift, right? And we'll talk about that later. But otherwise, that's our simple solution right here. Right? Well, the first year computer science student might say, okay, well, let me go ahead and let me go ahead and make this a little bit more, or a little bit less abstract right now. And just let's say that it's 3 and n here is, say, 64. Right? So not large here, but 3 to the 64 is a pretty large number. But when we mod out by, say, 100, then it's only a 2-digit number. Right? So a first-year computer science student may say, okay, well, I'm just going to go ahead and do this. Well, a to, or let's say 3 to the 64. Well, that's simply just 3 times 3 times 3 dot 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 times 3. There are 64 3's here, and thus 63 multiplications. Right? Computers are fast. Computers can do 63 multiplications pretty darn quick, right? So let's go ahead and try it. Right. In fact, yeah, let's go ahead and go with 3 to the 64 mod 100. There we go, 81. So, internet's slow, but computers are fast. This computer, that whatever Wolfram Alpha was using, it got its answer pretty darn fast. So, the first year computer science students, given this task, hopefully they would answer the following. Okay, I'm just going to go ahead and go with math.pow 3 to the 64. In fact, let's put these into numbers. Int a is equal to 3, int n is equal to 64, int m is equal to 100. And so the result, int result, is equal to math.pow. This is the best answer, right? Use a library. Right? And unfortunately, you're not going to be able to do that. Cast int to an int. Yep, we're going to have to cast that and then take the mod. There we go. And then system.out.println r, or f. R, sorry. All right, let's try this out. We got 20 probably because there's some round off errors here. So let's go ahead and get rid of this m here. Yep, it's not going to be able to do this because that's going to be overflow. Yeah. All right, so let's go ahead and go with something smaller, something that is a little bit more manageable. 12. And then we'll mod out by m. Hopefully this will at least give us an answer. 41. Good. Over here, 41. Okay. So there's the smart answer from a computer science 1 student. I don't want to compute it. I want to go ahead and use a library. Okay. All right. And then we already saw that, well, if you try to do it even for moderately large values, then you're going to end up with overflow. Right? So let's go ahead and go back to the drawing board and address both of those issues immediately. What I'm going to do is I'm going to use, as you saw up here probably, I'm going to use the big integer library. Big integer dot value of, our a is small, so we can use value of. Big integers are multi-precision integers. In other words, there's no overflow. If you do, if in the course of working with these things, it ends up with a larger number, more memory will dynamically be allocated to hold that number. So you can have arbitrarily large values. It's just that you're going to start paying for it and seeing a really big slowdown because everything is done in software instead. So big integer n is equal to big integer, or new big integer, because this is going to end up being a very big number eventually, 64. Okay, a small number so far. M is equal to big integer dot value of, and then we had 100. Okay. So again, the smart answer, a smart ALEC answer, if you want, is to use the library big integer dot mod pow. You can take a to the n mod m, and it returns a value. Big integer result is equal to this. So system.out.println r should be mod pow. Oops. It should be a raised to the n mod m. There we go. So let's go ahead and see if this works. With 64, what was it again? So it's 81 over there, 81 over here. Good, right? So what's the little bit less than smart answer? In other words, what if you're not allowed to use a library? You have to actually program this yourself. Okay, so the idea is, well, okay, we'll go ahead and do it this way. I'll go into a for loop. For I, running from, say, 1 up to, how many multiplications are there going to be? There are going to be 64 multiplications. But if so I'll go up to n minus 1. So if I initialize r here to be a, all I need to do is r is equal to whatever value I've got so far times a, and then here's a trick. You can mod out each time to keep it small. Instead of having one really growing large number and then taking the modulus at the end, you can actually mod out on each iteration here, and you'll end up with the same answer. So all this is doing is initially it's a, right? So 3. Then on the first iteration, you multiply it by a again. You multiply it by a again, multiply 63 times, or n minus 1 times, and then you output r. Right? That's the brute force, naive, direct approach. So let's go ahead and try it out. Public static big integer. We'll do our own mod pow. All right, there we go. And then a, we'll take in a, n, and m. Okay. There we go. So I'm just going to translate this pseudocode down here that you can still see. Big integer result is equal to big integer, or let's go ahead and go with a. Right? It takes on the value of a. By the way, big integers in Java are immutable, so every operation that you call on them, like mod pow here, returns a new big integer. Once a is created, you can't modify it. So what I'll need to do for my loop variable here is I'm going to need to create an index value, and I can start it at 0, right? And then for, or while, let's say, let me see. All right, actually I started at 1, right? According to my pseudocode here, I started at 1, so I'll go ahead and be consistent about that. And I'll go into a while loop here just because I can. You know, the way that you compare, you can't say that while I is less than m, because these are not numbers. What you have to do is you have to use the comparator pattern, dot compare to n, and that'll return something negative, 0, or positive, depending on the relative ordering of the values of I and n. So while this is less than 0, this means that I will be less than n. So less than or equal to is what we want? No, we want less than because we're going up to n minus 1. So we're going to stop 1 short. Okay? All right, what I'll need to update my I, of course. So usually you write your loop before you actually write your loop body. So I'll go ahead and take care of that here. I is going to be equal to I dot add 1. You can't do it like this because 1 is a regular old integer, and you have a big integer. If you want to add, you need to add another big integer. And so for convenience, 1, 0, and I believe 10 are stored in static variables in that class. So all I'm doing is adding 1. That's my basic loop right there. And then I'll return R when I'm done. R gets updated to R times A mod M. So R times multiply A dot mod M. Right? So you can chain these together because it has what's called a fluent design pattern that it returns itself, or that, well, actually no, it doesn't return itself here. This is not technically a fluent design pattern because it's returning a brand new object here, and then I'm calling a method on that brand new object here, and it's giving me another object. So there are actually several objects here instead of returning itself. But it's basically kind of very similar to the fluent design pattern where you can chain things together, dot, 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 dot. All right. Okay. Let's go ahead and try it out. Big integer. I guess, yeah, I'll just go ahead and reuse R. And then I'll do my multiplication demonstration here. Dot mod pow of A, N, and M. And I'll go ahead and output it. Let's see if we get the same answer. Do we agree? Looks like we're good to go here. And remember, it was 81. 81, great. 64 is kind of small, though. Now, 3 to the 64 is rather large. But let's go ahead and do some keyboard mashing here. Oh, too much mashing. There. Now, I will bet you $1 million that, maybe I shouldn't bet too much because OBS is taking most of my CPU right now. But I bet you $1 million fake internet dollars that this is actually going to execute rather quickly, and that this is actually going to execute rather a little bit slower, a little bit. 23. All right, let me go ahead and see if that's right. I'll go ahead and put it over here in Wolfram Alpha. What was it again? 23. And Wolfram Alpha says 23. So I have every confidence that the Java big integer library is correct. You can see by the stop symbol down here that this is still going. Okay, so should I waste your time here waiting for this to actually execute? Or we'll go ahead and let it execute in the background here. While we do, let's think about this. Okay. A to the N mod M. What is our input? Well, again, with algorithm analysis, you can have multiple inputs. Our input here are 3 numbers, right? Usually you simplify it. So that you're only looking at one number. You can choose the largest number or the most relevant number. In this case, for our particular algorithm, the most relevant number is n here, because we have a for loop that iterates n minus 1 times. Right? And so the size of A isn't going to matter that much. The size of M isn't going to matter for that much. From the perspective of that for loop that we just wrote, N is what is controlling the performance of that for loop, not A or M. So I'm going to restrict our attention here to N. What is our input size? It's not N. It is log N. The number of bits, or if you wanted to go log base 10, the number of digits needed to represent N. When I had 64 over here, right, my input size was not 64. It was 2 numbers, 6, 4. I'm not giving it this many things. I'm giving it a number that I don't even know how many characters that is. Let's see, how many characters is that? Character count, 40, and so about 58. This is a 58-digit number. That's its input size, 58. It's not whatever ungodly number this happens to be, if it even has a name. All right, I'm sure that it has a name, but I don't know what it is. I don't know. Does Wolfram Alpha tell us what name this is? It's quite interesting if they do. Ah, there we go. 6.49 octodecillion. Right, there we go. So it does have a name, and you learned something today at least. Every day learn something deep, every day learn something trivial, and so hopefully you're learning both of those things today. But that's our input size. So when we go to analyze our elementary operation, our elementary operation over there was, say, this multiplication. Right? How many times are we executing that? Right? So step 4. We execute n minus 1 multiplications. Right? That's pretty straightforward from that for loop. We execute it for 1, 2, 3, 4, all the way up to, but not including n because we stop 1 short, because we start our value r at a. We could have started our value r here at 1 instead, and then multiply it, but we'd have to go exactly n iterations there. Right? So we're skipping out on at least 1. So 5, what is this going to be? Well, okay, well that looks linear to me, right? Order n, right? Linear. By the way, it's still running. Clearly not, right? This is not linear because what is the actual input size here? Log n. Call that big N. Now big N is our true input size here. So what is order n with respect to our actual input size here, big N? Well, to solve for little n so that I can plug it in over here, all I have to do is raise this to the 2. Right? Because this is implicitly base 2. So to solve for little n, all I need to do is exponentiate this. And now you can see why this is taking so long. It's exponential in the number of bits required to represent it. Right? That's the true input size here. This will take, literally, this will take centuries to compute. I'd have to actually do a benchmark here of how many multiplications I can actually do. I'd also want to stop OBS to grab back some of my CPU power, although I guess it would be, it's not multi-threaded, so it's probably using a full processor right now. But it's still going to be exponential. You are, even on a supercomputer, you are probably going to be computing this program for centuries. Right? Versus, we already know that Wolfram Alpha can do it in a matter of seconds, minus the bandwidth, like instantaneously, essentially. We already know that Java can do this instantaneously. So how is it doing it? How is it working? Let me go ahead and stop this so that it doesn't interfere with anything else in the computer. We need to take a divide and conquer approach. So let's look at that again. Let's go ahead and look at some small number here, a to the 64. Right? Well, let's go ahead and do a divide and conquer strategy here. In fact, I'm going to regret writing it over here. Let me go ahead and write it in the center of the page here. Okay. What if I divided this into 2 problems? What if I said I need to compute a to the 32nd and a to the 32nd, and then I can multiply them together to get a to the 64th. Okay. I've divided it into 2 problems. This is a much smaller problem because this is only, if I use my naive algorithm here from that perspective, over here I was requiring 64 multiplications. Over here I'm requiring only 31 multiplications. And guess what? I can reuse those multiplications over here. I don't have to do this entire tree that's hanging off of this one because I've already done the computation over here. So I can just simply use one multiplication to multiply itself back. But let's go ahead and continue with the divide and conquer strategy. This is a to the 16, a to the 16. And you can see why I chose 64 here. This is a to the 8th, a to the 8th, a to the 4th, a squared, and just a times a. Right? And note here that I'm not drawing the entire other trees over here. If I had drawn all these trees, you could have seen that at the very bottom there are going to be 64 a's here, and consequently 63 multiplications to bring them all together. Even more multiplications to bring them all up from this original tree up here. But I don't have to do that. If I go and take a times a, that's a squared. That's one multiplication, right? One right here. Now I've got a squared. I don't need to compute all of those other a squares here. All I need to do is go a squared squared to give me a to the 4th. That's 2 multiplications right here. Continue doing that. A to the 4th squared is going to be another multiplication, a to the 8th. A to the 8th squared, a to the 16th, with one multiplication, a to the 16th squared, a to the 32nd, with just one multiplication, and a to the 32nd squared finally gives me the answer that I'm looking for, only with 6 multiplications. Rather than an exponential number like this tree illustrates, I'm doing the depth of the tree. That's 1, 2, 3, 4, 5, 6 multiplications, and that's it. In other words, log of n, where n is the number of bits to represent n. Now this is linear. No, linear, that's log, right? But remember that the input size is log n. So if I say that something is order log n and that's my input size, that's saying it's order log n, big N here. That's my actual input size, and that's why it's linear. Okay? That's the idea. Well, I chose 64 because it made a nice pretty picture where I could divide everything evenly. But what about a to, I don't know, the 77th? Right? As from the notes. Well, all right, that's a to the 64th. Let's think about this in terms of powers of 2. Times a to the 8th, that gives me 72. Times a to the 4th, that gives me 76. Times a, right, to the 1st. And I will keep that up there to be explicit about it. Right? Hey, those are powers of 2. I can use that idea that I was using before to compute powers of 2 easily by only doing repeated squaring. A squared squared to get a to the 4th. Square that another time to get a to the 8th. Well, if I square it another time, I get a to the 16th. I don't need that here. But eventually, I do need it in order to compute 64. Write this out with a bunch of coefficients. A to the 64th, the coefficient here is simply going to be 1. Times 0 times, okay, not times here, but let's see. Let me go ahead and rewrite these. This is a to the 1 times 64. I wanted the coefficient up here so that they don't disappear. Times a to the 0 times 32. Right? I can compute a to the 32, but but it won't contribute to this power here, and so I just can go ahead and multiply that by 0. That becomes a to the 0 becomes 1, so that it doesn't make the entire thing 0 like it was about to do over there. Right? So a to the 0 times 16 times a to the 8th, or sorry, 1 times a times 8, because I do need it, times a to the making sure I'm not missing any here, to the 4th, times a to the 0 times 2, right? That's the power of 2 between these two, times a to the 1 times 1. Right? Now look at these coefficients in the exponents here. 1, 0, 0, 1, 1, 0, 1. Guess what? That's 77 in binary. Right? So that gives us a hint as to how to do this for arbitrary numbers here. All we need to do is do repeated squaring, and then look at the binary representation of the number that we're actually trying to, the exponent of the number that we're actually trying to compute. If that number is 1, then I need to make sure that I save that, or save that in the form of multiplying that to some result. When I go a squared, well, I don't need that except for the next computation to do a to the 4th, and so I won't it won't affect this number up here, but I still need to square it to get the next number. I do need it, so I go ahead and multiply it into my result up here, square it to get a to the 8th. I need that, so I multiply that into my result over here. Square it, but I don't need it, so ignore it. Square it again, but I don't need it, so ignore it. Square it again, and I do need it, so I go ahead and put it up there. Right? This all suggests a very straightforward algorithm. all you need is a binary representation of the number that you're trying to do, and then a simple for loop or a while loop, however you want to write it, and keeping track of two numbers: the result and the repeated squaring value. Let me go ahead and get over to my pseudocode here. There we go. This is also called repeated squaring or fast binary exponentiation. Binary exponentiation because, of course, we're using the binary representation of a number, and so I mean, we could use a ternary and then instead of squaring things, we could do power cube things instead, but that's weird, right? So let's go ahead and identify our input here. My input is going to be A, M, and B, or N, sorry. And then I'm going to just write out the binary for this. B sub k minus 1. These are the high order bits, and then B1, B0. These are the low order bits. So these are all zeros and ones, and all you're doing is taking n and getting a binary representation of it. If you're actually, in fact, on your second assignment, you do actually code this. Of course, you don't have to have an explicit binary representation. What we're going to be doing is we're simply just going to be looking at each one of these bits. So you can do bit twiddling, where you are shifting these down and then only taking the lowest order bit in order to get B sub 0, B sub 1, etc., etc. Right? But our output here is going to be A to the n mod m. So here's my term, and I'll initialize it to A, and that's the thing that I'm going to be squaring every single time. And then of course I'll have a result. So how do I start that out? If the lowest order bit is 1, then I will start my result at A. Else, I'll start my result at 1. And that's just whether or not you want A to the 0, or sorry, A to the 0? No, A to the 1, right? So this is going to be 2 to the 0, or A to the 0, so that's going to be 1, or A to the 1, which would be A. Right, there we go. So this is just the initialization right here. So for I, running from the next lowest order bit, we go this way. We start at B1, and then we go up to K. Right? So we're starting at the lower order bits and moving to the higher order bits. And again, if you wanted to do this in programming, all you do is shift it down and then take the lowest order bit. So and it with 1 or something like that. Bitwise and with 1. Depending on the programming language that you're using. All right. So I will square my term. Is going to be whatever the term was before, squared, mod m. Because, of course, again, we want to keep it small every single time. And then if b sub I, the bit that we're looking at right now, if that's 1, then I make sure that this term contributes to my result up here. Result is going to be the result times the term, and then again, every iteration you can go ahead and mod out by m to keep it small, instead of doing it getting one really, really giant number and then at the end making it small. Works out mathematically because of math, right? So output R. There we go. And that's it. All right. So I will leave you to program that. If we want to revisit this tomorrow, then we can go ahead and look at it in Java maybe. But again, it's clearly this is going to be the multiplication. Multiplication down here is my elementary operation. But now instead of running for 1 up to n, right, we're running for 1 up to k, where k is the number of bits, which is approximately log base 2 of n. And so this ends up being order log n. It's not logarithmic like binary search, but it is linear with respect to the actual input size here. Okay? And that's how Wolfram Alpha was getting it so fast. That's how the big integer math library down here was getting it so fast. And by the way, I was going to demonstrate this in Python, but apparently the built-in times operator is naive, or it's just taking way too long. So I don't know what's up with that. Instead, I would probably have to pull out another library like NumPy or something like that, NumPy. I don't know how you pronounce it either. If anybody knows or wants to comment, I've always pronounced it NumPy because it's number pi, Python. So I guess it should be pronounced NumPy for Python, but it sounds better if it's NumPy, right? All right. Let's go back. All right, so we looked at repeated squaring, fast binary exponentiation, and I might update the notes later on that. But what I want to do is I want to again go through another example, in fact another 2 examples if we have enough time today, of demonstrating how you can use divide and conquer approaches to avoid work. It's kind of again, it harkens back to the brute force algorithms that we were looking at, and pruning, saying that that's never going to lead to a valid solution. So I can go ahead and prune that out and never look at that. The tree that I drew earlier, that's basically the same thing, recognizing, wait a second, I don't have to repeat the work that I used to calculate a to the 32nd. I don't have to repeat that all again. I can reuse that and take a divide and conquer approach, and then build the actual algorithm was not actually divide and conquer written as like a recursive algorithm like some of these others are. Instead, it looked at a divide and conquer tree, and then okay, well, I can get this by simply just going up one branch of the tree. So I'll start at the bottom and then I'll work my way up. Right? Okay. So let's look at one more example, and we'll take that example from math again, because again, computer science is math, computation is math, everything is math, right? Science is math. STEM, really, if you want to take all STEA and collapse them all down to math, everything ends up having or using or being math. Math is everything. So what I want to do is I want to take you back to grade school here for our next example. All right. Let me go ahead and give you 2 numbers here, 785 and 132. Right? Now, the grade school way of multiplying these together, in fact, you don't even use C dot, you use something like this. Let's go ahead and use the grade school method of multiplying these together and keep track of the operations as we're going. So we've got 2 3-digit numbers. That's our input. Okay. Let's go ahead and count out how many 1-digit multiplications are needed. Because, I mean, you might be able to do this in your head. Certainly the answer is to do this on a calculator or a computer or something. But if you had to do this on a piece of white paper, or if you were a computer that had to do this using a bunch of bits, right? How many multiplications would you end up doing? So 2 times 5, carry the 1. 2 times 8, 16, plus the carryover, and then carry over another 1. 2 times 4, 2 times 7, and then add in the carryover, and it's 15. Right? How many multiplications did I do there? 1, 2, 3. So at least 3. Right? Now I do 3. 3 times 5, and then remember that you shifted over, so you automatically put in a 0 here and a 0, 0 here. So 3 times 5, that's 15. Carry it over. 3 times 24, that's 25. Carry the 2. 3 times 7, 21, 23. There we go. So 1, 2, 3 more. What about the 1? Well, 1 times 5, 1 times 8, 1 times 7. So that you get 785, and then, but those were multiplications there. Even though it was 1, we could just carry everything down. You did have to do a multiplication there if you were a computer, right? So in other words, 9 multiplications. And you can kind of see this pattern. If I gave you 2 n-digit numbers, for the first one, you'd need to do n multiplications. For the second digit, you would need to do n multiplications. Third digit, n multiplications. Fourth digit, n multiplications, etc. So this is going to lead to n times n squared multiplications. And again, what we're doing here is 1-digit multiplications, because that's what our elementary operation is, right? And if you said that your elementary operation was just one multiplication of two arbitrarily large numbers, then you're kind of making it trivial. Now you're saying that the size of those numbers doesn't matter. It takes the same amount of time. Write down 2 3-digit numbers, and then write down 2 64-digit numbers, and see if you take up the same amount of paper in order to do those operations, and you'll find that you don't. Right? So 1-digit multiplications ends up being our elementary operation, and so this is going to be order n squared. N squared algorithms are bad, right? They are not fast, as we've already seen. Now, for the vast majority of numbers, though, you're not dealing with a lot of large, million, quadrillion, 50 million digit numbers multiplied by another 50 million digit number as a matter of course, right? So that's why computers are actually small. 32-bit numbers. If you the vast majority of use cases, the values that in an integer are not going to exceed 2.147 billion. And so those are the things that are optimized on hardware. Of course, then you can go to a 64-bit number because frequently we do have need for larger numbers. And then if you need to go higher than that, then you need to bring in a library to do it, right? And it's kept small because all of this stuff is done in hardware. These are all just wires that give you that instantaneous performance when you're actually on a computer. But if you have arbitrarily large numbers, you need to start doing stuff in software. So you need to start looking for much better solutions than n-squared algorithms. Okay? All right, I'm going to show you some magic. All right? So let's go ahead and do 47 times 51. Right? This is the multiplication of two two-digit numbers. So in other words, we would have to end up doing 4 multiplications of 1-digit numbers. Okay? What I'm going to do is I'm going to break this up. First of all, 47 can be represented as 10 to the first plus 7 times 10 to the 0. Right? Times 5 times 10 to the first plus 1 times 10 to the 0. All I'm doing is splitting this up into single-digit numbers that are then multiplied by some power of 10. Now, you might think, well, wait, what are these multiplications right here? No, they're not. They're simply shifts. If you want to multiply something by 100 or by a multiple of 10 or just 10, let's say, then all you need to do is shift things over, right? We used that trick when we went to the next line, like the 10 spot, the 100 spot, the 1,000 spot. All we did was draw a bunch of zeros without even thinking about it. That was not one of our elementary operations. We don't even need to think about it. It's just a shift. Now, when you go to program this, say, if you were to program this in a computer, you wouldn't think in base 10. You would think in base 2. And so there, a bit shift represents a multiplication by 2 or a division by 2. Right? In any case, these multiplications don't count. Right? We still have a multiplication here of, well, we still have 2 two-digit numbers, but I've broken it up into 4 one-digit numbers. Now, how can I do some magic here? Magic is nothing more than FOIL. Hopefully you remember that acronym. First, outer, inner, last. All you need to do is take the first one here, 4 times 10 to the first, times the first one here, 5 times 10 to the first. That's our F. Our O is going to be, and this is plus, 4 times 10 to the first, times 1 times 10 to the first, 0, sorry. Right. And then I plus 7 times 10 to the 0 times 5 times 10 to the first. And then our L is going to be 7 times 10 to the 0 times 1 to the times 10 to the 0. All right. I'm running out of space here. I'm going to give myself a little bit more room here. Well, look at these two. 10 times 10, that's just another shift. So this is actually 4 times 5 times 10 squared. That's really only one multiplication there. Plus 4 times, and then this one is just 1. So when I combine these, I'm getting 4 times 1 times 10 to the first. Plus 7 times 5, 10 to the first. Plus 7 times 1, 10 to the first. 10 to the 0 in this case, sorry. All right. Make sure that I'm correct there. 7, 4, 7, yep. There we go. And then we can actually combine these two. This is actually equal to 4 times 1 plus 7 times 5 times 10 to the first. There we go. So how many multiplications here? There's 1, 2, 3, 4 multiplications of 4 single-digit numbers. Okay. That's basically the grade school method right there. Right? Can we do better? Okay. Well, wait a second. What is this thing on the left-hand side over here? This is, or you know what? What do I want there? I always confuse myself on this one. So forget about the powers of 10 here. What I want to do is I want to get a hold of this. In other words, I want to avoid 2 multiplications if I can, and only do 1 multiplication. So what I'm going to do is I'm going to take, what is this thing equal to? 4 times 1 plus 7 times 5. All I need to do is take these 2 terms onto the other side, and I've isolated this one. So what does that look like? That looks like 4, let's see, yeah, 4 plus 7 times 1 times 5, or 5 times 1 to keep it in order, sorry, minus 4 times 5 minus 7 times 1. There we go. So instead of doing 1, 2 multiplications over here, I can do 1, 2, 3 multiplications. So, I've increased my number of multiplications by 1. Nope. I can reuse this multiplication right here, and I can reuse this multiplication right here. And instead of doing 2 multiplications, I only have to do this 1 multiplication right here. So these 2 multiplications go down to just one more multiplication. And all of these are single-digit numbers, right? This 4 and 7 single digits. This is plus right here. Sorry, this is plus right here. This is a multiplication. Now, technically there will be overflow over here, but if you take two n-digit numbers and add them together, you can only ever end up with at most n plus 1 digit number. So it's not going to blow it up like multiplication does. It only increases it by a constant factor. So there's 1, 2, 3 multiplications. Okay. I still don't get it. Right? How does that help us? How that helps us is by taking this to another level. Right? Instead of just going from 2 down to 1, let's go from n-digit numbers down and divide and conquer. So A is equal to given. Let me rewrite this. Given A and B, both n-digit numbers, I can split them up. Suppose that I wrote down A and it looked like this, and I cut it in half. If there were n-digit numbers to begin with, then here there are going to be n divided by 2 digits. Right? And what I'll do is I'll give those names. I'll say that it's A1 times 10 to the n divided by 2. Right? What I'm doing is I'm taking the digits here and then I'm chopping this part off. But I'm remembering that, well, it's actually larger than that. Oh, I need to multiply this by 10 to the n. Right? But if I take just a1, that's that's going to be an n divided by 2 digit number plus a naught. So a1 and a naught are 2 n divided by 2 digit numbers. All right. We'll do the same for b. b1 times 10 to the n divided by 2 plus b naught. And again, b1 and b2 are 2 n divided by 2 digit numbers. All right, so I've not bought myself anything yet. I started with 2 n digit numbers, so like 2 n digits total, and now I've got 4 numbers that are each n divided by 2 digits. So I still have 2 n digits. I haven't gotten rid of any digits here. But what I can do now is I can do the same FOIL trick. And let me go ahead and write that out. What is a times b now? Right. Well, again, if I took this representation and this representation, I would have a1 times 10 to the n divided by 2 plus a naught times b1 times 10 to the n divided by 2. Did I write out? No, I'm not writing 10 to the 0 here, just for to have less to write, basically. But it is there implicitly. Now I apply FOIL here, and I get a1, b1, 10 to the n. Right? Those 10 to the n divided by 2's, they combine into 10 to the n, plus a1 times b naught, 10 to the n divided by 2, plus a naught b1, 10 to the n divided by 2. That's the I. And finally, the L is going to be a naught b naught. There we go. Make sure I'm right. Yep. Now what I can do is I can expand this. Don't lose your other terms here. a1, b1, 10 to the n, plus. Now I'm doing the trick of taking these other two onto the other side, and I've got a1 plus a naught, b1 plus b naught, minus this one, a1, b1, minus this one here, a naught, b naught. There we go. So I've expanded out that middle term right there. And then I've got a coefficient 10 to the n. That's the coefficient. Then I've got 10 to the n right there. Plus a naught, b naught. Right? Now, let's count up the number of operations and how big they are. I'll move this up here. There are 1, 2, 3, and I'm reusing 1 and 2 right here. There are 3 multiplications of n divided by 2 digit numbers. All right. Dot, dot, dot. Well, eventually you get down to the end where you've only got, if you take a number and you divide it into 2, like if you start out with 100-digit number, now you've got a 50-digit number, then 25-digit number, then 12-digit number, and a 13-digit number. How do you handle that? Then a 6-digit number, then a 3-digit number, then a 2-digit number, and a 1-digit number. Eventually you get down to where you've only got two 1-digit numbers. That's your base case for the divide and conquer. Okay? So really quickly, how do you handle it when you've got, say, a 100-digit number and a 50-digit number? Well, you can pad it out with zeros out front without changing its value. And then when you recurse, you end up, oh, well, this is 0, and so I can immediately say I'm not going to recurse anymore because 0 plus anything I don't need, or multiplied by anything is going to be 0. So there are tricks to make sure that this is evenly divisible. You can go up to the next power of 2, so that if you've got two 5-digit numbers, just go up to the next power of 2, which is 8, by padding each with 3 digits in front of it. Right? Those are just technical issues. This is the idea, and it's called Karatsuba multiplications. All right. Again, we let A and B be 2 n digit or In fact, it was called Bidget, but it sounded weird, so they just shortened it to bit. But that's where we get the term bit. It's from Bidget, binary digit. But we've got two n-digit numbers. Let's set up our recurrence here. And in fact, I'm going to use m. Let m sub n be the number of one-digit multiplication made by Karatsuba on two n-digit numbers. Okay. To set up our recurrence here, remember that we end up doing 1, 2, 3 multiplications recursively, but they're each half as big. The number of digits has been cut in half, right? So that's going to be 3 multiplications, but on inputs that are half as big. Right? What about the non-recursive costs here? Well, as far as multiplications are concerned, shouldn't have thrown that over there. We're not doing any non-recursive multiplications here. This is a recursive multiplication. This is a recursive multiplication. This is a recursive multiplication. Otherwise, these are not multiplications here. This is a shift by 10. This is a shift by 10. So you could consider that to be a non-recursive cost. We certainly do have a bunch of additions and subtractions, which are additions, but because it's just an addition by a negation. So we've got 1, 2, 3, 4, 5, 6, yeah, 6 additions here. That's probably actually more than the grade school method, but in the grand scheme of things, multiplications are far more expensive computationally than additions, because multiplication is nothing more than iterated addition, right? If you look at it from an algorithmic point of view. But as far as multiplications are concerned here, we're not doing any non-recursive multiplications. So yes, it is 0 here. You're not doing any non-recursive, or you're doing non-recursive work, but you're not doing any non-recursive multiplication work. And that's what we're focusing on here. So what does the master theorem tell us here? A is 3, B is 2. What about D here, or K, or whatever we identified it before? 0 is going to be theta of 1. It's constant. Right? So what's the exponent here for n to the d? Well, what gives us a constant here? It's going to be 0. Okay? And finally, we now have an example of the master theorem that leads us to something that isn't just case 3 or whatever it happened. Case 2, I guess. Because if we look at this, this is 3 versus b to the d, 2 to the 0. This is now strictly greater than. Right? And so by the case 3 of the master theorem, I forget what it is, it's going to end up being that m sub n is theta n, or big O, of n to the log base b, in this case 2, of a. So let's come over here to Wolfram alpha, because I don't know what that is. Log base 2 of 3. Right. So this is, I'll change it to big O here, of n to the, there we go, 1.585. 585. Yeah, I went higher. I went higher than Wolfram alpha here told me, because this is obviously going to be an irrational number that goes on forever. So to say that it's theta of that, you'd have to leave it in this form, which is perfectly fine. Or you go a little slightly higher if you want big O and want a terminating number here. Right? Well, that looks better to me. Remember that the naive way of doing this was order n squared. We've cut this down now to order n to the 1.585 by simply doing some grade school math and applying a rule that you probably learned in middle school or something like that. FOIL, right? How to multiply two sums together, right? This is due to Karatsuba. What do I have a year on this? According to my information, 1960. In fact, throughout the 50s and 60s, there was an entire, because computers were just coming in, there was an entire movement to try to improve basic operations like that. Because if you could improve multiplication algorithmically on a computer, then that automatically made, because multiplication is used so much, that automatically made everything much faster. So you focus on the most common operations and how can we do this even faster? And you look for faster and faster ways of doing this kind of stuff. And there are a whole bunch of developments in the 50s, 60s. There's the Tomb-Cook algorithm, which is, again, another basic divide and conquer style algorithm of order. It got it down even lower, and to the 1.465, right? And then various other operations have got it down even further. What's the holy grail? The best possible. Well, trivially, you have to look at the input. So you have to look at all the bits. I mean, unless you're going to do some probabilistic thing or put in some assumptions on the nature of the numbers, or you just want a heuristic or an estimate or something. To get an exact multiplication, you are going to have to look at every single digit. And if n is the number of digits in each one of those numbers, then you do have a lower bound here, a trivially kind of lower bound of order n. So Karatsuba was n to the 1.585, right? Dot, dot, dot. There's the fast Fourier transform, FFT. You might have heard of that before. It's used in signal processing all over the place because it's super fast, and discrete fast Fourier transform. It got it down to log n log n. And then there's another term here, n log n. There we go. There's there's a variation on the fast Fourier transform. I don't know if it has a name or not, but it's due to Fuhr in 2007. That's I think that there was even another improvement more recently. I forget what it was, but there's n log n, and then there's this iterated log n to the log star n, and I'll let you look that up to check to see what that is. It's basically a special function that how many times do you have to apply the log function to get down to 1. So with 64, for example, what is the iterated log of 64? Well, if I apply log of 64, I get 6. If I apply log of 6, I get 2 point something something, dot, dot, dot. So if I apply log of 2 point something something, then I get down to 1 point something something. Then if I apply another log of that, then I'm finally down to 1. So it's the iterated log function here is even super slow growing with respect to the log function, and then of course it's 2 raised to the iterated log function. This is super slow growing. So, but it is better than log because it would be log however many times it takes to get that down to 1, right? So that's an improvement. There was, I believe, another improvement more recently. I have yet to read the paper, and it might have been restricted, but you can see that there's been progress. Now, fast Fourier transform is used all over the place in real systems, and especially in signal processing systems. But these are kind of impractical in that you only see a speed up of n squared down to 1.585. You only see an actual practical speed up with extremely large numbers. For small numbers, it's not going to be, especially if it's just a built-in integer in your language, you're not going to do any of this stuff. You're just going to go with a times b, a asterisk b, right? Because it's hardware. It's hardware that's doing it. It's super fast. It's just a bunch of wires that have been hard-coded for those particular operations. You can always build a bigger computer with more wires and do 5084-bit operations all on the chip if you want to, making it super fast because it all runs in parallel. Whatever you can make it run as fast as 64-bit processors. But that's specialized hardware that does exist for specialized applications. But In general, these are algorithmic approaches that are of theoretical interest, and you're paying at that point. You're paying more for the recursion than you are getting back savings from having to do fewer multiplications. Okay. All right. One more idea, right? And at this point, I channel my one of my old professors. In fact, I'm not. I'm just going to introduce the idea. Maybe we'll get back to it tomorrow. But matrix multiplication. So you see the kind of the logical progression here. I started out with the multiplication of one number, exponentiation. What about the multiplication of two numbers? Now what about the multiplication of a collection of numbers? If I have a matrix A and I want to multiply it by a matrix B, and each one of these is n-digit numbers, and we're restricting our attention here to square matrices, then this produces a matrix C, which again is n by n. So these are two n by n just matrices multiplied together. Now, using just the straight up definition of matrix multiplication, if each one of these has a sub ij entries, right? This is one particular entry over here, and there's another particular entry over here, b sub ij, right? And that produces some other entry over here, c sub ij. C sub ij is actually going to be a vector. The way the matrix multiplication works, hopefully you've seen it before. If not, that's okay. You take a row here, the ith row, and then you take and you transpose it over here, and you take the jth column. And each one of these n numbers, which is in a row, and each one of these n numbers, which is in a column, they're multiplied together, and you sum them all up. Okay, running from 1 up to n of, you take the ith elements in the ith row, so a sub I, and then k running for each one of these elements in here. And then you multiply it by b sub j is running from 1 down to n from the top to the bottom. Or sorry, k is. And then j. All right, this is the jth column over here. That's the straight up definition there. So how many multiplications? How many additions? For doing it naively like this. In fact, this is something I frequently assign in Computer Science 1 to illustrate two-dimensional matrix usage. And we don't assume, even there, we don't assume any linear algebra background, but we give this definition. All you need to do is take the ith row, figure out the jth column. Here it is. It's just a simple for loop. But you have to do it for n squared entries in C. Right? So how many multiplications? Well, for k running from 1 up to n, there's 1, 2, 3, 4, right? So for each entry, there are n multiplications, right? How many additions? Well, technically there are only n minus 1 additions, because after you get the first term there, then you're just adding all of the other terms. So there are n terms. So if you start with the first one and there are n minus 1 left, then there are only n minus 1 additions for each entry. There are n squared entries in the result. So that leads to a total of n cubed multiplications and n squared n minus 1 technically. We'll just go ahead and say I don't care about that. N cubed additions. Right? So we've got a cubic algorithm here. And if you thought that, if you finally, hopefully if you bought that quadratic algorithms are terrible, cubic algorithms are going to be even worse. So there's always been a holy grail of finding a better solution. What is the best possible? Well, if there are n times n squared entries, well, you have to look at them all. Now, there are instances that you can, like sparse matrices where there are lots of zeros, or other certain types of matrices that are specific to a problem, and then you can get away with faster multiplication because you know that there's some symbolic solution or something like that. You can always look for shortcuts like that. That's what problem solving is about. Those are domain specific problems though. So if we want to do this in general and we have to look at every single entry, then order n squared is the best we can do. So there's a gap there. This is the naive approach. N squared is the best possible. Again, from that perspective. Can we bring it down to n squared? So if you say that the input size is going to be n squared, instead of n, it's perfectly reasonable to say that the input size is n squared because you actually have n times n, you have n squared entries. Go ahead and say, just like we did before with the bits, that my input size is actually n squared. And so that if this is not exactly linear, but this is order, what is it going to be? My real input size, 3 divided by 2. This is going to be order n, my real input size. So can we bring this down to this? I'm going to do it in these terms though, right? Because this is easier to deal with. But technically it would be this. Okay. All right. We're running low on time here. So what I'm going to do is I'm going to take a picture. There we go. And I am going to channel my what was it? I think I was taking a PDE course, a partial differential equations course, or maybe it was differential equations. I forget. But I forget the exact scenario too. But I asked him a question. You know, he wasn't teaching this. He was teaching something else completely different. And I said, all right, well, the mathematician that came up with that theorem, what was he thinking about? I mean, how did he come up with that solution? How do you know that now I can kind of remember. How do you know? How did they know that that you could use that to converge to something? And the best quote that has stayed with me for the rest of my life is, well, you sit there and you stare at the equations for a while, and suddenly it comes to you. So, how did, this is Strawson's multiplication now, how did Strawson come up with the following equalities that I'm showing, the following equivalences that I'm showing you right now, right? Well, likely he had a big giant blackboard, and he wrote down what the definition that I wrote down over here, excuse me, of matrix multiplication, and he just started moving things around and saying, just like Karatsuba multiplication, all he did was write down the FOIL rules and say, okay, well, if I move that over there, that over there, that over there, eureka, I can get away with only 3 multiplications here. Here is Strawson's matrix multiplication on a 2x2 matrix. Remember that this is, the C over here is our result. And if we've got a 2x2 matrix here, then we can label them as A sub 0, 0, A sub 0, 1, A sub 1, 0, A sub 1, 1. Likewise, B over here. All he did was write down these numbers, right, manipulate them and move them around a little bit, and he came up with the following equivalences. That ultimately what we would have to do up here is A00, 0, that's equal to, and I'm going to use my own fingers here, that's equal to taking this first row right here, or sorry, not A00, 0, C sub 0, 0 is equal to, take that first row, A sub 0, 0, and multiply it by the first column, B sub 0, 0, plus A sub 0, 1 times B sub 1, 0. Right? All I'm doing is taking this first row and multiplying it by this first column, and then summing them up. And did I get it right? Yep, I got it right. All right. And then he wrote down, you know, C sub 0, 1, C sub 1, 0, and C sub 1, 1. And so he had 4 equations. I'm not going to write them all. But he realized that there's 1, 2, 3, 4, 5, 6, 7, 8 multiplications. 2 to the third. 8 multiplications. Then he started moving stuff around and saying, you know, factoring things out. And finally he came up with the following equivalences. That C sub 0, 0 can actually be written as M1 plus M4 plus M5 plus M7, where M1, M5, or M4, M5, and M7 are defined down here. And you can see that what he was thinking about when he started writing these on a blackboard, coming up with equivalences, he was looking at ways that how can I reuse stuff, just like Karatsuba was. Hey, I don't have to multiply that product twice. I can go ahead and reuse it. For example, M4 right here is used here, and it's used over here. M1 is used here and here. M3 is used here and here, etc., etc. So some of these things are being reused. But the key is, instead of 8 multiplications, you only have to do 7. 1, 2, 3, 4, 5, 6, 7. The rest of these things are additions or subtractions, which are basically additions. They're additions by a negative number. So we have blown up the number of additions. Remember, the number of additions before was going to be what? 2 to the 4th times, yeah, 2, so 4 additions, right? Over here, 1, 2, 3, 4 additions. Here we end up doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 additions, subtractions. We'll go ahead and say that they're the same. We do a lot more additions at the but we pick up 1 fewer multiplication. Now, does that help us? I'll save that for tomorrow. I'll go ahead and end it on this today. But I just wanted to, every year when we cover Strawson's matrix multiplication, I still wonder. He didn't write in his paper. Maybe he did. I've not read the original paper. No mathematician, once they get the idea, they present it, they publish it. They don't ever tell you about the failures, right? And this goes for life. So if you want a life lesson here. I think that the best quote that I've seen on the internet is that when you see somebody else's successes, you're seeing their highlight reel, right? You're not seeing the hundreds or many hours of failures that it took to get to that point. We're not seeing that with Strawson. Wow, you came up with this brilliant mathematical equivalence that cuts out 1 multiplication and makes matrix multiplication faster. Awesome. How did you do that? Did you, some brilliant idea that came to you, or some fundamental mathematics? No, plug and chug. He would probably just sat there for hours upon hours, recombining things and saying, okay, well, that didn't work because now I've got 10 multiplications. Tried something else. I still have 8 multiplications, until finally he came upon something. Oh, 8 multiplications. Yeah, there are 10 more additions, or there's a blow up in additions, but I'm trying to optimize this for multiplications, right? That's how all these things work. You never see all the failures that go behind all the successes. So that's something to keep in the back of your mind. Every time you're looking at some success, it's not that they got there automatically and that they're better than you, they're smarter than you. It's just that they worked hard. And you yourself, that's what you need to do. You need to work hard, accept that you will fail 100 times before that final brilliant idea, the 101st time, right? You just can't stop at the first time or the second time or even the 99th time. You have to go all the way there. And hopefully that's advice for the rest of your life too, right? All right, so thanks for watching today. I will come back tomorrow and we'll conclude with we'll conclude divide and conquer kind of strategy.